In this part of the lecture, I wanted to remind you that we are in the course of organic reduction and in the lesson about soil fertility management, as you see in the slide. I am Professor Giovanni Dulia. We're still here speaking about soil properties. Previously, I spoke about soil profiles, soil horizons, how they differ in the color, which is the reason why they have different colors, how the organic matter influences the color of the horizons and the color of the soil. I mentioned previously that usually in the most of the agriculture soils, the organic matter is 1.5%. But we have other cases when the content of organic matter is very high, it exceeds 20 to 35%. In this case, it is considered organic soil material and the soil is called organic soil. As this material is mostly devoid of mineral soil material, they cannot be described in terms of soil texture. However, the following texture terms can be used to describe organic soils. So we have three kinds of organic soils. The first one is called peat, which is organic material in which the plant parts are still recognizable. What does it mean? This means that if we see the peat, we can see still parts of a plant that are not decomposed. Then comes to muck, which is highly decomposed organic material in which no plant parts are possible to be recognized. And the third one, which is mucky peat, where decomposition is intermediate between muck and peat. This is based on classification that used United States Department of Agriculture. Continue to speak about soil properties and about physical properties of the soil. Now I want to speak you to explain what is the soil structure. It's not so easy to define or to understand it if we have not a real example. But let's remember that we spoke about soil content and we spoke about particles. So these small particles of the soil can be aggregated together and then create some structural units that we call pads. Then these pads are organized into a repeating pattern and then it is referred as a soil structure. Between the pads and are cracks called pores through which soil, air and water are conducted and take the place of each other. Soil structure is most commonly described in terms of the shape of the individual pads that are present within a soil horizon. So let's see different soil structures that we can find in different soils. So you have granular structure, which are roughly spherical like grape nuts. Usually the size of them is 1 to 10 millimeters in diameter and most of them are found in A horizons. where plant roots, microorganisms, and sticky products of organic matter decomposition can bind soil grains into granular aggregates. Then comes the platy pads that are flat pads which lie horizontally in the soil. Platy structure can be found in A and B and C horizons. It commonly occurs in A horizon as the result of compaction. Then comes the other type of pad that is blocky, which is roughly cube-shaped with more or less flat surfaces. If edges and corners remain sharp, we'll call it angular blocky. If they are rounded, we'll call it subangular blocky. Sizes commonly range from 5 to 50 millimeters across. Blocky structures are typical of B horizons, especially those with a high clay content. They form by repeated expansion and contraction of clay minerals. And then we come to the prism, to the prismatic pads, which are larger, vertically elongated blocks, often with 5 sides. Sizes are commonly between 10 to 100 millimeters across. These prismatic structures commonly occur in frangipans. Columnar structure or columnar pads, there are units which are similar to prisms and are bounded by flat or slightly rounded vertical faces. The tops of columns, in contrast to those of prism, are very distinct and normally rounded. Here in this image you have an interesting demonstration how the structure of the soil looks like when it's a very good soil with a good structure. As I explained before, the structure is nothing else than different granules created by particles which are staying or placed side by side to each other. And just imagine that you have, for example, some seeds that are put in the container. Between these seeds, since they are, let's say, as granules that we see here in this image, they create pores. But in this case, we have structure by structure creation of small and big pores or large pores. In the large pores, the tendency is that they are most of the time with air, and the small pores, when there is humidity, are full of water. In the large pores, the water cannot stay for long because the gravity that tends to bring the water in the lower horizons of the soil profile. But not all the soils have a good structure. Not all the soils have particles which are organized or attached together, aggregated together to create pads, and then pads which create other organizations staying side by side to each other, as explained in the previous slide. We have cases that we have a massive, compact soil which has not separated two beds of any kind. These massive structures are found in clayey soils, and usually they have very small pores. They have slow permeability of the water or for the water, and in this case, they have poor aeration. The other extreme soil that we consider without structure, there are single grain soils, which are found in very sandy soils where every grain acts independently. It is separated from the other, so there is no binding agent to hold the grains together into pads. In this case, permeability is very rapid, in contrary to the massive compact soil, but the fertility and water holding capacity are low. And in this image, I wanted to demonstrate, or I wanted to illustrate what I was speaking about the structure before. In fact, here in this image, I wanted to show you how the structure of the soil, except the other properties, can influence how the water is behaving in the soil. Is it going in the deepness of the soil, or it goes through the runoff to the water streams? So when there is precipitation, the water arrives to the biomass, to the plants or trees or forest, as in this case, and then a good part of it arrives to the soil, onto the soil, and through runoff or infiltration will move further. When it's not, how to say, the soil is not filled with water, water through infiltration go to the soil, into the soil, and through percolations go to the deep groundwater table or to the stream. The runoff or the water that comes through the runoff, the same, is going down the slope to arrive to the stream. So when the soil has good structure, it has a good permeability. This means that what quantity of the water will go deep in the soil profile will arrive to the groundwater and a part of it to the water stream, and a lower quantity of water will go through runoff to the water stream. In cases when the soil is very compact, very few water will go through infiltration to the soil. I mean, through the soil profile in the deepness of the soil. When the soil is compact, it's very compact, most of the water will not enter it, and in fact, it will go through, as I explained, through the runoff to the water stream. So now we can understand how it is important, the structure of the soil. Of course, there is not only the structure of the soil that influences in the fate of the water on the soil, but the structure is very important, or is one of the important properties of soil.